Drag reduction system. The DRS button operates the drag reduction system, opening the rear wing flap by 85 millimeters to reduce drag and increase straight line speed by 10 to 12 kilometers per hour. This legal cheat code becomes available when drivers get within 1 second of the car ahead in designated DRS zones. Press the button, the wing opens, and suddenly the following car becomes a missile closing at frightening speed. Teams position the DRS button based on driver preference. Some mount it on the steering wheel's front face for thumb operation. Others prefer placement for index finger activation. The button includes LED indicators showing DRS availability and activation status. The system automatically deactivates when drivers brake or exit DRS zones, preventing them from keeping it open through corners and launching into barriers like impromptu aircraft. DRS transforms overtaking from pure driver skill into strategic warfare. Drivers time their approaches to detection zones like precision snipers, positioning themselves within the 1 second window at exactly the right moment to maximize overtaking advantage on the following straight. Skip 110 preset. The Skip 110 button manages critical control sensors throughout the car and power unit, acting as a shortcut system for accessing predetermined settings without cycling through multiple menu options. This button allows drivers to jump directly to specific configurations during high-speed sections when menu navigation becomes impossible. Teams program this button with different presets for various track conditions and race situations. Wet weather presets might prioritize stability and predictability, while dry conditions allow more aggressive settings favoring outright performance. The skip function prevents drivers from manually scrolling through dozens of options while battling wheel-to-wheel at 300 kilometers per hour. The system integrates with the car's central processing unit, instantly applying complex parameter changes across multiple systems simultaneously. One button press can adjust brake balance, differential settings, high energy deployment, and aerodynamic configurations in milliseconds. Gearbox neutral. The neutral button disengages the transmission, allowing the car to stop without stalling the engine or damaging gearbox components. F1 cars don't have traditional park positions like road cars. They rely on this electronic neutral system for stationary periods during pit stops, grid procedures, or garage operations. Engaging neutral becomes critical during pit stops when mechanics need to work around stationary cars with engines running. The button prevents accidental movement that could injure mechanics or damage equipment. Teams position this control prominently but with sufficient protection against accidental activation during racing. The neutral system also serves safety functions during incidents. If cars become stuck in gravel traps or barriers, neutral prevents transmission damage from continued wheel rotation while recovery vehicles extract the car from dangerous positions. Pit lane speed limiter. The pit limiter button ensures cars cannot exceed pit lane speed limits, typically slower than 50 miles per hour, though varying by circuit. When engaged, the system overrides throttle input using engine mapping rather than brake intervention, maintaining legal speeds regardless of pedal position while allowing drivers to maintain optimal racing lines into pit boxes. The limiter activates through engine power reduction rather than mechanical braking, preventing jerky deceleration that could upset car balance during pit entry. This allows drivers to carry speed through pit lane corners while automatically maintaining legal velocities on the straights, where speed cameras monitor compliance. According to racing drivers, the button features sunken positioning to prevent accidental activation during high-speed racing. Accidental pit limiter activation at 300 kilometers per hour would create dangerous speed differentials with following cars, potentially causing catastrophic accidents. Pit confirm. The pit confirm button alerts the pit crew that the driver intends to pit on the current lap, triggering immediate preparation procedures. This communication becomes critical during strategic battles when split-second timing determines whether pit stops gain or lose positions relative to competitors. Teams monitor this button constantly during races, as pit confirm signals initiate complex choreographed sequences involving tire warmers, fuel calculations, and mechanic positioning. The button prevents miscommunications that could leave drivers without prepared pit crews or result in unsafe releases into traffic. Modern pit confirm systems integrate with team radio communications and telemetry monitoring. The button press automatically transmits the driver's pit intention while providing pit crews with updated fuel consumption data and tire degradation information needed for optimal service timing. Differential entry. The differential entry switch controls torque distribution between rear wheels, specifically during corner entry phases while drivers brake and turn into corners. More open differential settings provide better turn-in characteristics and improved steering response, but reduce stability under heavy braking loads. Entry differential settings dramatically affect how cars behave during the critical transition from braking to cornering. Locked settings provide maximum stability, but can cause understeer, making cars push wide and forcing drivers to scrub speeds through corners. Open settings allow better rotation but risk sudden oversteer if drivers push beyond traction limits. Teams create different entry maps for various track types. Monaco's tight corners require different entry differential settings than Spa's high-speed sections. Drivers adjust these controls throughout practice sessions, finding optimal compromise between turn-in performance and braking stability for each circuit's unique characteristics. Differential mid. The mid-corner differential switch manages torque distribution through corner apex phases, balancing maximum traction with cornering ability during sustained lateral loading. This setting determines how cars behave during the longest portions of corners where consistent balance becomes critical for maintaining speed. Mid-corner differential affects tire wear patterns significantly. Locked settings maximize grip but increase tire temperatures through scrubbing, while open settings reduce wear but can cause sudden handling changes if traction breaks away. Teams balance performance against tire degradation throughout stint lengths. The most sophisticated differential systems include load-sensitive mapping that automatically adjusts torque distribution based on lateral acceleration sensors. These systems provide optimal balance across varying corner speeds without requiring constant driver input during races. Differential exit. Exit differential controls torque distribution as drivers accelerate out of corners, managing power delivery to maximize traction while minimizing wheel spin. This becomes the most critical differential phase for lap time, as exit speed directly affects straight-line performance on following sections. Locked exit differential settings provide maximum traction for powerful acceleration, but can cause understeer that prevents drivers from using full track width. Open settings allow better car rotation and wider exit lines, but risk wheel spin that wastes power and increases tire wear. Teams program exit differential based on power unit characteristics and tire compound behaviors. High-powered engines require more aggressive locking to control wheel spin, while lower power outputs might benefit from open settings that prioritize cornering speed over pure traction. Engine braking. The engine braking switch adjusts how aggressively the power unit slows the car when drivers lift off the throttle without applying brakes. This system manages energy recovery while affecting car balance during deceleration phases, approaching corners. High engine braking settings increase energy recovery for ERS systems, but can cause rear wheel locking or unstable car behavior during corner entry. Low settings provide more predictable handling, but reduce energy harvesting efficiency, potentially leaving drivers with less electrical power for overtaking attempts. Modern hybrid power units integrate engine braking with MGU-K energy recovery, creating complex relationships between braking feel, energy generation, and car balance. Teams program different engine braking maps for various race situations, balancing energy recovery against driver confidence and lap time performance. Brake balance. The brake balance rotary switch shifts braking force distribution between front and rear axles in real time, allowing corner-by-corner optimization based on track conditions, fuel loads, and tire degradation. Typical setups run 56% front bias, but drivers adjust this percentage constantly throughout races. Higher front brake bias provides more initial stopping power and helps with turn-in, but increases front tire wear and can cause front wheel locking under heavy braking. Rear bias improves car rotation through corners and reduces front tire stress, but risks rear wheel lockups that can send cars spinning into barriers. The most advanced brake balance systems include brake migration technology that automatically adjusts distribution based on pedal pressure intensity. Light braking might use different bias percentages than emergency stops. optimizing performance across the entire braking range while maintaining consistent pedal feel. Mark button. The Mark button allows drivers to identify specific points of interest in telemetry data during practice sessions, qualifying runs, or races. When pressed, it creates timestamp markers in the car's data logging systems that engineers can reference during post-session analysis. Drivers use the Mark button to identify handling problems, aerodynamic issues, or setup irregularities that occur at specific track locations. The marked data helps engineers correlate driver feedback with objective telemetry measurements, improving setup changes between sessions. The marking system integrates with GPS positioning and sector timing, providing precise location data for each marked event. This allows engineers to compare marked issues across different cars, drivers, and setup configurations to identify systematic problems or optimization opportunities. Accept button. The Accept button confirms default modes selected by Skip 110 preset functions, acting as the Enter key for steering wheel menu systems. This prevents accidental setting changes while allowing drivers to confirm intentional adjustments during high-speed sections. The Accept function becomes critical when drivers need to change multiple parameters simultaneously. Rather than individually adjusting brake balance, differential settings, and energy deployment, the Accept button applies predetermined combinations instantly through preset packages. Teams program Accept functions with different confirmation requirements based on setting criticality. Minor adjustments might require single button presses, while major mode changes demand sustained activation to prevent accidental engagement during wheel-to-wheel combat. Race Start. The Race Start button configures the car's systems for maximum launch performance, optimizing power unit output, differential locking, and traction control parameters for getting off the line cleanly. This mode prioritizes acceleration over top speed, fuel efficiency, or component longevity. Race Start modes integrate clutch bite point settings, engine mapping, and differential locking to provide optimal traction during the critical first few seconds when grid positions can change dramatically. Wrong start settings can cost multiple positions or cause wheel spin that ruins entire race strategies. Teams practice start procedures extensively, with drivers memorizing exact sequences for different weather conditions, track temperatures, and grid positions. The Race Start button eliminates complex multi-step procedures, allowing drivers to focus on clutch timing and throttle modulation rather than system management. Radio button. The radio button activates push-to-talk communications with pit crews, providing the vital link for strategic updates, technical feedback, and emergency communications during races. Teams position this control for instant thumb operation without interfering with other critical functions during high-speed sections. Modern radio systems include noise cancellation technology, filtering wind and engine noise, ensuring clear communication at speeds exceeding 300 kilometers per hour. The systems integrate with FIA race control frequencies, allowing race directors to communicate directly with drivers during safety situations or regulatory matters. Some teams implement multiple radio channels with separate frequencies for different communication types. Engineering discussions might use different channels than strategic conversations, with drivers switching between frequencies using dedicated steering wheel controls based on information sensitivity and race situations. Strat Mode Rotary. The Strategy Mode rotary dial controls power unit modes affecting internal combustion engine performance, turbocharger boost levels, and fuel consumption rates. This single control manages multiple engine parameters simultaneously, balancing performance against component longevity and fuel economy throughout races. Different strategy modes include practice settings prioritizing reliability, qualifying modes maximizing single lap performance, and various race modes balancing speed with survival. Teams create specific maps for different scenarios. Wet weather modes emphasize drivability, while safety car periods optimize for energy recovery. The rotary design allows drivers to cycle through predetermined modes quickly without menu navigation systems. Each click position corresponds to specific engine parameters that teams have optimized through extensive dyno testing and simulation work. Menu Rotary. The Menu Rotary dial enables drivers to navigate through multiple information pages on the central display screen, adjusting various car parameters including radio volume, screen brightness, and telemetry displays. This control provides access to secondary systems without dedicating individual buttons to each function. Teams program different menu structures for practice, qualifying, and race conditions. Practice menus might emphasize setup adjustment options, while race menus prioritize strategic information and tire management data. The rotary system allows quick navigation through complex information hierarchies. Advanced menu systems include driver customizable layouts that can be modified based on personal preferences and specific track requirements. Some circuits demand constant tire temperature monitoring, while others prioritize fuel consumption or aerodynamic balance information throughout different race phases. HPP rotary. The HPP, or Hybrid Power Plant rotary, controls energy management systems including ERSK and ERSH deployment strategies, MGU-H operations, and battery state management. This dial manages the complex relationships between electrical and combustion power sources in modern hybrid power units. Different HPP modes include aggressive deployment for qualifying or overtaking, conservative harvesting for energy management, and balanced settings for optimal race pace. The system automatically adjusts energy recovery and deployment based on selected modes while allowing drivers to override for specific situations. The HPP rotary integrates with fuel mixture controls and engine modes, creating cohesive power unit strategies that optimize total system performance. Teams spend significant development time mapping HPP modes for different track characteristics and strategic requirements. LED indicators. The LED strip across the steering wheel's top edge provides critical shift point information and flag condition warnings through color-coded displays. The progression typically runs from green LEDs at lower RPM through yellow and orange to flashing red at optimal shift points. Beyond shift indicators, the LED system displays flag conditions communicated by race marshals. Yellow flags trigger yellow LED warnings, while red flags activate full LED strips to ensure drivers notice critical safety situations. Some systems include blue LED indicators for pit lane signals or DRS availability. Modern LED systems include customizable brightness settings that automatically adjust based on ambient lighting conditions. Bright daylight requires maximum LED intensity for visibility, while night racing demands reduced brightness to prevent driver distraction or vision impairment during dark track sections. Paddle shifts. The middle paddles between the steering wheel shift the 8-speed transmission, with drivers typically using right paddles for upshifts and left paddles for downshifts. These carbon fiber levers connect to seamless shift gearboxes that execute gear changes in milliseconds without interrupting power delivery to the wheels. Modern F1 gearboxes shift faster than human eye detection, maintaining acceleration through transitions that would snap necks if drivers weren't prepared. The paddles feature customizable positioning and resistance based on individual driver preferences. Some prefer fingertip operation, while others want full finger engagement. Each paddle activation triggers complex hydraulic sequences involving clutch disengagement, gear selection, and re-engagement, all coordinated through the steering wheel's central processing system. The technology processes more data per second than typical home computers while operating in environments that would destroy consumer electronics instantly. Clutch paddles. F1 drivers use dual clutch paddles only for race starts, tire warming procedures, or victory celebrations, with modern cars ditching clutch pedals entirely in favor of paddle-operated systems. Teams often provide 2 levers for bite point calibration and launch symmetry, though some allow single lever setups based on driver preference. Drivers can adjust bite point behavior directly via steering wheel controls during races if necessary, allowing real-time calibration of clutch engagement characteristics. The system typically requires pressing both paddles simultaneously to activate, then releasing one while maintaining the other to reach optimal bite point position. During race starts, drivers hold both clutch paddles while engines rev to optimal RPM. At lights out, they release one paddle immediately while gradually modulating the second based on traction conditions and wheel spin tendencies. The entire launch sequence demands split-second timing developed through thousands of practice starts. Overtake button. The orange OT button provides temporary engine boost for overtaking situations, giving drivers full power without requiring multiple adjustments across different systems. This system deploys ERS energy aggressively while maximizing internal combustion engine output, providing additional power for approximately 33 seconds per lap. The overtake knob can control different modes for defending positions or attacking other cars during overtaking maneuvers, with teams programming various deployment strategies based on race situations. Qualifying modes maximize single lap performance, while race modes balance power delivery with energy conservation. Using overtake early in race stints can leave drivers defenseless against attacks later when energy stores become depleted. The system integrates with fuel mixture controls and engine modes, creating temporary power surges that can determine the difference between successful passes and missed opportunities. Drink button. The drink button activates pressurized hydration systems pumping fluid, usually comprised mostly of water, into drivers' mouths via tubes. F1 races lasting over 2 hours in extreme heat with cockpit temperatures reaching 60 degrees Celsius make hydration critical for maintaining concentration and physical performance. The drink system holds approximately 1.5 liters of isotonic fluid with controlled flow rates, preventing choking during high-speed sections. Teams customize fluid mixtures based on individual driver preferences and race conditions. Hot weather demands different electrolyte balances than cooler temperatures. Without proper hydration, drivers experience decreased reaction times, reduced concentration, and physical exhaustion that costs championship points. The drink button might seem trivial compared to performance controls, but it often determines whether drivers finish races or retire with heat-related problems. Modern F1 steering wheels represent the ultimate interface between human ambition and mechanical perfection, with every button controlling systems that generate forces impossible just decades ago. These controls are manufactured using aircraft-grade specifications, preventing accidental activation, because at 300 kilometers per hour, there's no room for operator error or mechanical failure. Each wheel costs more than luxury cars while containing more computing power than early space missions, proving that peak performance demands absolute precision in every component.